management class. In project management, when time is no longer deterministic, or we can say this is probabilistic, there is a one technique that we usually use to determine the completion time, which is project evaluation and review techniques.
In the previous video, we already learned about the technique in project management, what we call it critical path method or CPM. Now, in this video, let's discuss another method that is complement the CPM, what we call it the project evaluation and review technique, or we can simply call it PERT. What is PERT in here? So, PERT is a method of analyzing the tasks involved in completing given project to identify the minimum time that is needed to solve, that is needed to complete the total project. As mentioned before, that PERT and CPM are complementary tools. And the difference between those two is the CPM is only employ one time estimation and also one cost estimation for each activity. Here, PERT utilize three-time estimates, three time estimation, and try to find out the minimum time. As we mentioned before, this is the purpose, to find out, to identify the minimum time needed to complete the total project. And in PERT, there is no cost for each activity. Historically, the PERT was developed for the US Navy Special Project Office in 1957 to support the US Navy Polaris nuclear submarine project. Just a brief story about the PERT. So, we mentioned before that there is three-time estimate PERT. First is the optimistic time. Optimistic time in here mean that if everything is going according to the plan, if everything is going smoothly according to what we planned before. The second is what we call it the pessimistic time. In pessimistic time, this is opposite with the optimistic time. This is assumed that we run in unfavorable condition, not go smoothly according to our plan. And the third time is what we call it the most likely time. This is actually the time in between those two, optimistic and pessimistic time. This is in average. Yeah, so most likely time. So we put an symbol, optimistic time as A, pessimistic time as B, and realistic one, most likely time as M in this way. The distribution of the activity time in PERT follow beta distribution, where we can put it in here, optimistic time on the left hand side, the probability of 1 in 100 of occurrence in this case, and then pessimistic time over here, and most likely time is the center, become the center. Based on this three calculation, based on of this three time in PERT, we can calculate the expected time following this formula, which is T represented the expected time equal to A optimistic time plus 4M, this is most likely time, plus B pessimistic time divided by 6. This is the expected time, and the variance is equal to B minus A divided by 6, and we should square it. So this is those formula to calculate the expected time and variance. So we can calculate, for example, yeah, for example, we have an activity, an activity. This is the example that we use in CPM. In the previous CPM, we use only one time, but here we use three alternative time. So optimistic, most likely, and pessimistic time. Based on those three times in PERT, then we can calculate the expected time using the formula that we just discussed before, and variance. We got all of this number. Previously, we said or we discussed that the activity time is following the beta distribution. But when we total, when we sum up the completion time, yeah, or the when we sum up the activity time and become the completion time, the distribution of the total project completion time will follow the normal distribution. So this is the difference. And each activity times are statistically independent. As you may see in here, that a project, for example, has the expected completion time is 15 weeks. Yeah, on 15 week with the standard deviation is 1.76 week. How we can calculate the probability of completion? Based on the formula, based on the situation in our previous example that the project expected completion time in 15 weeks and standard deviation 1.76 weeks, we can find out first is a z in here is due date minus expected completion time divided by sigma, and which resulted in the due date, yeah, the time expected, yeah, in here we actually questioning when we ask the due date, when the due date is, yeah, our data just mentioning there is expected completion time which is 15 week. What if, yeah, what if, or uh, what if the due date or the completion in 16 week, what is the probability we complete in week 16? So here the week 16 becoming the due date. So 16 minus 15 divided by 176. So it resulted 0.57, which resulted the in here the probability is from the normal standard table. We can see that 71.57%. So 16 week is around here, 16 week. So this is 16 week is around here. So the probability of completion, yeah, is the area or the region shaded on the left hand side, yeah, the left hand side. So the probability of the project completion time exactly the same with the date of completion time, expected date of completion time is 50%. Now let's talk about the crashing. In the situation where we need to shorten the project completion time with an additional cost because, for example, we need to finish the project because we need to complete it within this year, but actually based on our calculation this project should be completed next year, yeah, next year. We can do this, we can shorten the project completion time by the activity of crashing. Crashing mean in here put an additional resources on some activities to shorten the completion time of activity. Here there's a trade-off, yeah, a trade-off. For example, in normal time we can, for example, illustrate in this figure. In normal time we can complete the activity within 3 weeks with the cost of 30,000. We can do crashing and the time becoming 1 week by adding some more worker, more machinery, and so on. So we can complete those activity within 1 weeks with the total cost is for sure this is higher than the normal cost, which is 34,000. In here, we can calculate what we call it the crash cost per week, which is coming from the crash cost minus normal cost divided by normal time minus crash time. So 34,000 minus 30,000 divided by 3 minus 1 resulted in 2,000 per week. If we have all the information about normal and crash time, we can calculate all of the crash cost per week for all activity that is listed up in here. And note that not all activity is in the critical path. So what should we do in here is we should crash the activity only the activity on the critical path. So it's resulted the candidate, which is A, and then C, and E, and G, and H. So this is the candidate of crashing, because when we crash the non-critical path activity, it's useless actually. So based on here, based on the information, then let's take a look at the information of the crash cost per week. Let's find out the crash cost per week that is minimum, which we see in here's A activity A has the minimum crash cost per week. So the priority, we should crash the activity A first in this case. When we crash the activity A, for example, 1 week, from 2 in here becoming 1, the total completion time is no longer 15, but will becoming 14. Please note that when we crash the project, it might be there is a new critical path appear, not passing through this line. Of course, this line is still the critical path, so not only passing through this line, but there is a possibility there's another line become the critical path. So we should take a consideration and pay attention which path that becoming critical when we do the crashing. So thank you so much for joining me in this video discussing about the PERT. Let's continue discussion on how we can close the project in the next video. So see you again and thank you.
Thank you so much for joining me in Learning Operation Management. See you again in the next video.